Yeah. Nice. So now you just want to input this one into this equation. Sorry, board is low, I know. And then you can do also the same for time derivative, but it's simply just minus omega carré times W.
Oh, yeah. And it's twice. So.
Mm-hmm.
Wait, I'm not done.
Just do space for the moment, and we'll do time later.
Yeah.
Yes? So TT.
And I'd like to just finish that.
Yeah. So this one is W. WXX. Yeah, simply.
Yeah.
Good. So we are almost there. Here we've taken the special derivatives here, and now only remains this time derivative. You can use like time derivative here, so you know it.
Better do that.
dw dt. Yeah.
Right.
No, it's not same. This is omega, so it's minus I omega times W.
Oh, wait, that's W.
Yeah, it's not same. Yeah, it's close but not same.
Oh my god.
I omega. Yeah.
That's not good.
And there is I also. This, don't forget this I.
Oh man, this is bad.
So you can make a bar under the W to differentiate it.
Oh yeah.
It's not the same. See, like just a bar. So, yeah,
W.
that's it.
So that is minus.
It's actually minus omega squared. Because minus square makes 1, and this makes minus 1.
Oh yeah, the non-negative.
Yeah. There you go. So, you're almost there. So you've got
Pretty much thought to this.
omega. Yeah, I'll let you.
Omega W. Right.
So actually, it's you keep this sum, m squared plus k squared plus k squared times so bracket times minus times omega squared. The minus cancels.
Minus right.
No, they cancel. Because you've got 1 here and you've got 1 here, so they cancel.
Oh yeah.
Times W plus this term, so which is minus k squared.
W or is that?
That's W. Yeah. Yeah. N squared. And you're almost there. Now you want to express omega squared with respect to the rest. So we are almost there. Now we've got this equation, and what we want to do is express omega squared with respect to the wave numbers. Yeah. And so now you can cancel all the W.
Oh, yeah.
Yeah. Up. And you can just express omega square with respect to the rest. Equals. Yes. And last step, omega squared. Yeah, that's good. That's all good. And now we just have to put this on the other side.
Oh, you're from the other. Oh, right.
Great. Thank you. Thank you very much. That's good. Thanks. Good job. And now what we end up with is a dispersion relation for internal wave. And so, yeah, I'm just going to write it bigger. So what we've got here is a relation between so we see that we have this relation between the frequency, omega, and the horizontal and vertical wave numbers. And if we just make a plot of the wave vector here, so that we call k, it has a horizontal component, small k, and a vertical component, m, and we just call theta the angle of this wave vector with respect to the vertical, then what we recognize here, k squared over k squared plus m squared, this is simply sine squared of this angle theta. So this is a simpler way to write the dispersion relation. Okay? So this is really interesting properties because it shows that the relation dispersion do not depend on the value of the wave vector, but only on its angle with respect to the horizontal or the vertical. I recall that here we are dealing in a no rotation case, and this relation is a bit more complicated when we take rotation effects into account. But we are going to focus on this one here. So from this, there are lots of things we can learn about the internal rotate structure. So at first, so I just recall it up there. So there are already a few properties that we can derive here. So first of them is anisotropy. We can see that there is a favored angle of propagation for the internal wave, which is theta. So it means that if we fix a forcing frequency omega, for example, like the oscillating rod at a forcing frequency, and if we fix the background stratification n, then the angle theta is imposed as well. Okay, so there is anisotropy. And we can see as well that we have an upper limit for the forcing frequency of the wave because sin squared of theta is always smaller than 1, and therefore for propagating wave we have to have omega smaller than n. So the background stratification imposes a limit for the forcing frequency. So these are the two first properties. And then we can have a look at the phase speed and group speed of this wave. So this is definition of the phase speed, and using this dispersion relation or using this expression, we can derive the value of the horizontal group speed and vertical group speed here. And we can find that the scalar product is 0, which means that the phase speed and the group speed of internal waves are orthogonal. So this is an important property. The phase and the energy of internal waves, they propagate orthogonally, okay? So this is like on this this is what you saw in the movie, so something similar. You've got this oscillating rod. We generate some beams here. So energy is propagating. If we have a look at this beam, for example, energy is propagating in this direction, and the phase is propagating perpendicular to it. Okay, so energy propagates this way, and the phase propagates downwards and to the left. So which is shown here. And finally, we can have a look at what happens to the fluid particles. How will they displace in this field? So using simply the incompressibility equation, we can easily find that the phase speed and the fluid particle velocity are orthogonal. So consequently, the fluid particle propagates perpendicular to the phase speed or parallel to the group speed. So they propagate in the direction of the beam. So this is the group speed, if we've got a beam propagating downwards. So this is the group speed, and fluid particles, they'll propagate in the same direction as the group speed, while the phase speed is orthogonal. Make sense? Okay, so knowing all that, all these different and non-intuitive properties, we can have another look at an internal wave field and see if we recognize these different dynamics that we saw. So here I'm going to show an example of some lab experiments. So we are using the same technique, which is synthetic Schlieren, to observe the generation of internal waves. So the forcing is made by the oscillation of this ridge at the bottom of the flow. So periodic oscillation that mimics tidal forcing in a linear background stratification. So this is at the really beginning of the experiment. So here the ridge is not moving, but it is actually oscillating back and forth at an amplitude of 1 millimeter. And we can see that progressively, like a pattern emerges after a few periods of forcing. So period of forcing was about 10 seconds here. And we can see the generation of upgoing and downgoing internal wave beams. Okay? Can you see, so if we have a look at this one, can you tell me in what direction is the group speed? Propagation of energy. Here, okay? Toward the top and the left, okay? What about phase speed now? Can you see it here? Propagating downwards. So this is the phase speed. So here we are looking at density anomalies. So we don't see the fluid particle motion like with particle image velocimetry measurements, we could see them. And we would see that the fluid particles, they move, so it's starting again, in the direction of the group speed. And here you can see a reflection. So for the downgoing internal wave, you can see a reflection at the bottom here. And then going upwards with the same angle at the upwards going. Okay, so do you recognize the properties that we talked about, like propagation of energy and phase and fluid particle displacement? Okay. So this is here a series of experiments where we varied the forcing frequency from like really slow forcing to really fast forcing here. And we can see that we always follow this dispersion relation. This angle of the wave beam with respect to the horizontal is imposed by this relation here. And we can see that when increasing omega for a constant n, this angle progressively increases as well when we look at this upgoing beam. Okay. What we can also see here is that some more complicated dynamics happen here. In particular, can you see this secondary beam? So what do you think this can be? What can we say about the angle of this beam with respect to this one, for example?
Twice as big.
Yeah, twice as big. Thank you, Craig. So what we can infer here is that there are some harmonic effects into play here. So one of the assumptions we made is that it was a linear assumption. Okay, therefore we didn't allow for harmonics to propagate. But in reality, when we force at a given frequency, we are also likely to excite some harmonics motions. And this is what happens here. So this internal wave beam oscillates at 2 omega. Okay? And therefore, the angle is about twice as big. Yeah. That's it. Another thing that we can see is that we can see, one more word about this harmonic propagation here. We can see that it's most powerful when the angle of this harmonic beam matches the angle of the topography. So it indicates that the shape of the topography controls the energy input into the beam. Okay, we have kind of a resonancy process at play here, and which leads to a selection of for the generation of internal waves. So this is important for internal waves in the ocean because knowing the bottom topography and the stratification, we can have a good idea about how to localize a region of intense internal wave generation. We would look at region at which we have like such matching angles here. And we know that large amplitude internal waves would be likely to be generated in this region and therefore intense mixing. So yeah, back to the ocean here. So these isopycnal lines, they are disformed, but they take a particular shape, which is imposed by this generation of internal wave beams. Okay. So this is a bit of a summary here of the different physical properties that we discussed, dispersion relation. And here on this graph, what you show is dissipation rate epsilon that has been measured in the ocean, and that is an indication of how much mixing is happening in the ocean. And we can see, so these red patches correspond to zones of intense mixing, and we can see that they more or less follow this line, this black line here for the downward beam. So, and we can see that intense mixing happens on the path of internal waves. So this is kind of a way to picture the mixing that is induced by these waves. Okay, can you see these zones here that are on the path of the propagating internal waves? So group energy going this way, and group speed this way, and phase speed this way. Regarding force oscillation, I've been talking so far about tidal motion, but there are also other forcing at play. For example, we can have the interaction with, between a constant flow and a bottom topography that can also induce some internal waves that are stationary, that can be attached to the topography. So here you have some example in the atmosphere. So the interaction between this constant flow and this topography can create some turbulence and shear really close to the topography, but away from it, we generate some internal waves in the wake of the topography, and they are called Lee waves. one good way to see them in the atmosphere is to look for lenticular clouds that are formed due to the upwards and downwards motion of this Lee wave, and some regular patterns are present like that, and they indicate the presence of Lee waves. Okay, so down the lab we are doing some experiments to study these Lee waves and their impact on the ocean mixing. So this is one picture that had been taken from one experiment by Bishak and Anton here. And this is one of the labs. So some of you did this lab yesterday, and some will do it today. And we can see here, so here the ridge is actually at the free surface, and it's pulled in the tank in a stratified background, and we observe the generation of Lee waves, so in the wake of the ridge, and some mixing that is associated with these Lee waves. And so far, when we describe oceanic processes, some parameterization are used to quantify this mixing that occurs at really small scale. And what we would like to do is to try to refine them and like provide more realistic parameterization of it. So yeah, this is a movie of one experiment that had been done the lab. So here, the different layers that are colored with different dyes permit to show the wave motion when the ridge is crossing the tank. So can you see here, so generation of regular waves here, and all these blurry regions, they indicate that mixing is happening. And this is what we want to quantify. Okay, so we can see that these waves are attached to the topography, and that's why they are stationary, and so they decay when getting further away from the topography and down to the bottom here. A bit more time, yeah? Okay, maybe 5 minutes and then a bit of time for questions. Okay, so to finish with, maybe a word about propagation of large amplitude waves in the ocean. So when we talked about internal wave beams, one strong assumption that we made is a linear approximation. But when we don't do this approximation, we allow for large amplitude waves to propagate, and what is interesting is that they can propagate in the ocean and also in the atmosphere in a stable manner. So we are going to try to see why. These solitary waves, they propagate in the ocean, they propagate in the pycnocline that acts as a wave guide for the propagation of this large amplitude wave. They can propagate over distances of like 200, 300 of kilometers before breaking and mixing the pycnocline and this region here. So they can take big amounts of energy away from the generation zone. And so that's why it's also important to understand where they are generated and how much energy they can take away. So there are mainly two generation processes in the ocean for the generation of solitary waves. One of them is what we call primary generation. So for this process, it's the interaction between a flow, like it can be a tidal flow as we discussed before, and the topography, which create large amplitude motion in the pycnocline that is at the top of the topography. And this large amplitude motion, they can evolve into solitary waves. So this is one process. And the other process that has been discovered more recently regarding this solitary wave generation is a secondary generation. It has been observed, for example, in the Bay of Biscay, and actually researchers observed the propagation of solitary waves, but really far away from any rough topography. So they made the assumption that it was probably another mechanism at play here for the generation of these solitary waves. And actually they could relate the region of generation of this wave with the location of the impact of an internal wave beam on the picnic line. So remember the beams we are talking about? When they impact on the picnic line, they can generate some large amplitude motion that evolve into solitary waves. So this has been observed first in the Bay of Biscay, but other occurrences have been observed in the Atlantic, for example. Okay. Formation of a solitary wave. So, as I said, they can be really stable and propagate over large distances. And so, in this scheme, we can try to understand why they can propagate in so big distances. So imagine large amplitude sinusoidal waves that propagate. Because it has a large amplitude, which means that its amplitude is similar, for example, to the top layer depth, then nonlinear effects will come into play and will provoke a steepening of this wave. If there is only a steepening, the wave will eventually break. But you've seen that internal waves are dispersive, and this dispersive effect will tend to slow down the front of the wave, and then it will prevent steepening. So this is this balance between nonlinearity and dispersive effect that will sustain the wave and keep it stable so that it can propagate over long distances. Okay, so this is like kind of simple way to understand the stability of this large wave. So dispersive effects are really important here. Okay, I think I will conclude here. So we've talked about variety of regimes. So linear regimes to start with, we've seen the physical properties of propagating internal waves, like phase speed and group speeds that are orthogonal, and propagation as beams. And so this was in the bottom ocean. And then we had a look at what happens in the picnic line, in the top ocean. So we were heading for more nonlinear cases in a stronger picnic line. So we can see that when varying these two parameters, like the linearity of the flow and the strength and the type of the stratification, more generally, we can observe different regimes of propagation for these internal waves. And yeah, I think I will stop here. Thank you.
Would a typical angle, like radial angle, be like 1 or 2 degrees or more?
It's a few degrees, yeah.
So the pictures are kind of been 60 degrees.
Yeah, that's it. Yeah, in lab experiment we can get the angle that we want, but typically in the ocean it's less than 10, I would say.
So the waves that popped out on the big decline of the ocean. So you said that they transport a lot of energy away from the source region. How important are they in the ocean for the ocean dynamics, these solitary waves? Are you able to put a number on how important they are, how much energy they propagate away?
I can give like some order of magnitude of amplitude. So in the Sea of Zulu, for example, solitary waves of 200 meters depth have been observed, and this is the depth, the order of magnitude at which mixing of the ocean picnic line will occur. And the amount of mixing that happens is yet to be quantified. Yeah. But because it's large amplitude, so it can be, sometimes the amplitude of these solitary waves can be compared to the depth of the mixed layer. So it can really vary the depth of the mixed layer by a factor of 2.
But locally they're clearly important, but in the big scheme of things in the ocean circulation, are they important? I guess that's what I really meant. Was really the question I meant to ask. Are they just in curiosity? Like in the atmosphere, I think they're a curiosity.
Yeah.
They occur and they're spectacular and really interesting. But as far as the dynamics of the atmosphere are concerned, they're probably inconsequential. But I think you're making implying for the dynamics of the ocean they're probably more.
In region of generation of solitary waves, the dynamics of the mixed layer is mostly affected by the breaking of these solitary waves. Yeah. So, like how much it depends, and so it varies with. It has a seasonal variation because the strength of the mixed layer plays also a role in the efficiency of this generation process. So, therefore, the dynamics of the mixed layer depends on the amount of mixing, which depends itself on the amount of solitary waves that can be generated. Yeah. So yeah, there are various steps. Yeah.
Just to get a bit of the scale of this as a newcomer, so how deep is the mixed layer, and what sort of wavelengths are we talking about for the poetry one?
So depth is like of the order of 100 of meters, and it can be bigger than this. And the typical wavelength, so that depends on the strength of the pycnocline. It's mostly controlled by the density jump in the pycnocline, but it's less. 25 kilometers is a good approximation for it. Yeah. Between 25 and 50. And excuse me. Yeah, and in the ocean, so here in this scheme there is only one deep trough, but in the ocean, solitary waves are generated in trains of troughs that are ordered by a decreasing amplitude. And in this train, the balance between nonlinear and dispersive effect is reached. So there can be like up to 20 of these troughs in a train.
Is it known like what kind of amount, for example, in the atmosphere has to be to generate significant enough big waves for things like rolling to the cloud, but also things that do have consequences like rotors and stuff like that? What sort of, in that same sense, in the atmosphere, does a bit of topography have to reach before it will affect? Is it just above the mixed layer where it comes stratified?
So what matters here for the efficiency of the Lie wave generation is a Froude number that compares. So Froude number, which is U over NH. So U is the velocity of the flow, N is the local stratification, and H is the height of the topography. So this controls the dynamics of the Lie waves. So it means that the height of the topography depends on the local stratification for a constant U. But typically, like for hills of few hundred of meters, you can observe Lie waves over. But yeah, it depends also on the stratification.
Okay. I think we might draw this to a close if there's no other questions. Yvan, thanks very much.
Thank you.